Welcome back to the Deep Dive. It is Thursday, February 5th, 2026. And today we are doing something a little different.
Yeah, we are.
Usually we take a stack of articles or, a trending news topic, maybe something about the latest VR headsets or climate tech, and we just tear it apart. But today we are looking at a map.
A roadmap, to be
Yeah.
precise. And not just any roadmap. We have in front of us a document that is, let's just say it's circulating through the CTO offices of pretty much every Fortune 500 company right now.
It's called the 2026 Enterprise DevOps Roadmap.
That's the one.
And it sounds a little bureaucratic, doesn't it? Like something you'd find in a dusty binder next to a fax machine.
It does have that ring to it.
But when I started reading this, I realized it's actually, it's a survival guide. It's a curriculum designed to take a novice, what this document calls a cadet, and turn them into an architect.
And an architect in 2026 implies something very different than it did, say, 3 or 4 years ago. We aren't just building systems that run code anymore. We are building systems that think, systems that act.
We're talking about the difference between a tool you use and a partner you work with.
Exactly. It's a fundamental shift.
It feels like we're moving beyond cloud native. That term feels so, 2023, doesn't it?
It really does. It's like saying World Wide Web or information superhighway.
Right.
Cloud native was about where the code runs. It was about containers and orchestration, sure, but it was still a very manual process at its core. The conversation today, and what this roadmap is laser focused on, is agentic orchestration.
Okay, agentic orchestration.
It's about self-healing systems. It's about the shift from humans managing machines to humans designing machines that manage themselves.
Which brings us to the mission of this deep dive. We are going to explore how a developer or an operator evolves to meet this moment. Because the roadmap identifies a very specific, and I think a very dangerous trap that the industry has fallen into.
They call it the paper engineer problem.
I love this term. It's a little bit stinging, but it's so accurate.
It hits close to home for a lot of people, I think.
It does. When I read it, I laughed, but then I kind of winced. For the listeners, let's define a paper engineer. Because it's not about being qualified on paper, it's about the depth of your reality.
Exactly. So think about the last few years. We've built these incredible internal developer platforms, or IDPs, the drill.
Yeah.
You log into a beautiful dashboard. Maybe it's Backstage, maybe it's a custom portal. You click a button that says deploy database,
Yeah.
and poof, magic happens.
It feels like magic. You have a database, a load balancer, a URL. You didn't have to touch a server. You didn't have to configure a single subnet.
Right. And that's the trap.
Yeah.
A paper engineer is someone who is an expert at operating that dashboard. On paper, they look like a senior engineer. They can deploy complex microservices. They can scale applications with a slider.
But the moment the abstraction breaks,
That's it. The moment that magic button throws a 500 error or the database locks up and the dashboard just gives you a spinning wheel, they are paralyzed.
they're the pilot who can fly on autopilot but has no idea how to land the plane in a storm. They know which buttons to press, but they don't know what the buttons do mechanically.
That is the perfect analogy. They've never been in the engine room. They don't know what's happening under the hood because the tools have been so good at hiding it.
And the argument here is that in 2026, when we are relying on AI to do the heavy lifting, understanding that engine room becomes even more critical.
Absolutely. Because if the AI makes a mistake and you don't know how the kernel works, you are completely helpless. You can't debug the AI.
So this roadmap proposes a solution that seems almost, regressive, but in a good way. It argues for a bottom-up pedagogical approach,
It says, stop teaching Kubernetes first.
which is ishy in some circles.
Yeah.
The boot camps all start with Intro to Kubernetes.
It is heresy,
Ah.
but the argument is sound. It says before you touch a Kubernetes pod, you need to understand the Linux kernel. Before you let an AI handle your rollbacks, you need to understand the statistics behind continuous verification.
You have to earn the automation.
You have to earn it. You have to know the rules before you can let the machine break them for you.
So we have a journey ahead of us today. We are going to walk through 6 distinct phases outlined in this roadmap. We're going to go from the engine room, the gritty, low-level stuff, all the way up to what they call the nervous system, where the AI lives.
And just to set the technical stage, the
Yeah.
backdrop for this is a very specific, very modern 2026 toolchain. We aren't speaking in abstracts here.
Right, this is concrete.
We're talking Linux, Azure, GitHub, SonarCube, JFrog, Terraform, Harness, and Dynatrace.
A powerful stack. It's basically the gold standard for enterprise right now. So listeners, put on your hard hats. We are going down to the basement, phase 1, the engine room.
The foundations. This is where you can smell the oil and grease.
Okay, so the source material starts with a statement that I think is designed to start a fight in a bar. It says, containers do not exist.
It's one of my favorite technical truths. It sounds like a Zen koan in it. There's just no spoon.
It really does.
But if you actually look into the Linux kernel code, the source code that runs the entire world, you will not find a struct or an object called a container. It simply is not there.
So we've been living a lie. We talk about containers as if they are these little shipping boxes, but they aren't real objects in the OS.
In a way, yeah. What we call a container is actually a user space illusion. It's a magic trick performed by the kernel using two very specific primitives. And if you don't understand these two things, you don't really understand containers.
And those two things are?
Namespaces and control groups.
Okay, let's dismantle the illusion. Let's start with namespaces. The roadmap describes this as answering the question, what can I see?
Correct.
Yeah.
When you run a process on a Linux server, let's say a standard web server like in Jinx, normally it has a godlike view. It can see every other process running on the machine. It can see the entire file system. It can see all the network interfaces, which is terrifying from a security standpoint.
Yeah.
If I'm running my Banks app and some random game server on the same machine, I definitely don't want the game server seeing the Banks file. Exactly. If that web server gets hacked, the attacker can see everything. A namespace puts blinders on that process. It creates a little slice of reality just for it.
And the most critical one, according to the roadmap, is the PID namespace. PID stands for Process ID.
Right, and this is the one that causes the most confusion for cadets. Every program running on your computer has a number, right?
Yeah.
Your browser might be process 1024, your music player might be 500, and so on.
Sure.
Now, this is the trippy part. Inside a Docker container, your application thinks it is PID1. PID1 is the boss. It's the admin process. It's usually systemed or init on a normal server.
So the application feels very important.
Very important. It looks in the mirror and sees a king. Look at me, I'm PID1. I run this entire world. It's the king of its own little castle.
But it's a very, very small castle.
It's a closet. Because if you, the admin log into the host machine, the actual server underneath, and look at the process list, that same web server might be PID 4500. It's just a random, unprivileged, unimportant process floating in a sea of thousands of other processes.
So it's living in a simulation, the matrix for processes.
Precisely. And that's the security feature.
Yeah.
This is what prevents lateral movement. If that process gets hacked, the hacker looks around and sees nothing, just itself. It can't signal or kill other processes on the host because in its reality, they don't even exist.
It's like being in a solitary confinement cell that you think is the whole world.
That's a perfect description.
That's PID. Now, the roadmap highlights another namespace that I think trips people up even more, the network namespace.
Oh, the source of so many headaches. So the network namespace gives the container its own slice of the networking stack, its own IP address, its own routing table, its own local host, its own little private internet.
And the roadmap uses the Kubernetes pod as the classic example here. I think many people assume a pod is just a fancy wrapper for a container.
A very common misconception. A pod is actually a shared network namespace. Think of a pod like a tiny studio apartment.
Yeah.
And the containers inside that pod are roommates.
Okay, I like this analogy. Roommates in a studio.
Because they share that namespace, they share the IP address, they share localhost, they share the network card, essentially. So if roommate A, container A, decides to listen on port 80, maybe it's the web server.
Then roommate B can't.
Roommate B, container B, cannot listen on port 80. It's physically impossible. The line is busy.
And if you don't understand that underlying concept that the pod is the namespace, you will spend days debugging.
Days.
Yeah.
You'll be staring at your config saying, why is my second container crashing on startup? It's crashing because the port is already taken. That is a paper engineer trap right there. They are looking for a network error in the cloud provider when the error is actually inside the namespace logic.
Okay, so namespaces cover what can I see. The second part of this illusion is control groups, or C groups. And the roadmap says this answers the question, how much can I use?
Right. This is the economics of the system. Namespaces provide isolation. C groups provide rationing. And in 2026, the industry has finally, thankfully, standardized on C groups v2. This allows the kernel to strictly ration resources, CPU, memory, and I/O.
Let's talk about the CPU controller first, because I think people assume if the server has free CPU, their container gets to use it. That's how my laptop works. If I open a game, it takes all the CPU it needs.
A very dangerous assumption in a multi-tenant cluster. With C groups, we set quotas. You might have a limit defined in your Kubernetes YAML, let's say half a CPU core. If your container hits that limit, the kernel literally stops scheduling. It throttles the process.
Wait, even if the host machine is sitting there, 90% idle. Even if their spare cycle is just going to waste.
Yes, it does not matter. A contract is a contract. Your application will start lagging, requests will time out, and you'll look at the host metrics and say, but the server is empty. Why is my app so slow?
And the answer is the perk group.
The cook group is enforcing the limit. It's brutal, but it's fair.
It's necessary. Otherwise, one rogue process could eat the whole server and take everyone else down with it.
Exactly. It prevents the tragedy of the commons. But the one that really scares me, and the roadmap highlights this as a kind of horror story, is the memory controller. Specifically, the killer.
That sounds like a slasher movie villain, the kill.
It acts like one.
Yeah.
The out-of-memory killer is the kernel's bouncer. If a container tries to consume more RAM than its group group allows, the kernel doesn't just say no or slow it down. It calculates something called an score, identifies the offending process, and instantaneously kills it.
Like sick kill.
Sick kill. No warning, no goodbye, no graceful shutdown, just gone.
And if you're a paper engineer looking at your dashboard,
You just see your pod disappear. Or it restarts mysteriously over and over. You check the application logs. There's nothing. Because the application didn't crash, it was murdered. It didn't have time to write a goodbye, cruel world log.
so how do you solve that mystery?
You have to know to look at the kernel logs desk to see the OBRAM killer signature. That's a crucial distinction. Application logs versus kernel logs.
One more controller mention here, I/O. This is about preventing the noisy neighbor problem.
This is huge for databases and anything that writes to disk. Imagine you have a critical SQL database running on a node. It needs to write to the disk constantly to commit transactions. Then someone deploys a logging agent on the same node.
And that logging agent goes crazy.
It goes crazy writing logs. Without I/O controllers, that logging agent could completely saturate the disk bandwidth.
Starving the database.
The database just stops responding, not because it's broken, but because it can't get a word in edgewise. It's like trying to have a conversation in a crowded nightclub. cgroups v2 prevents that by rationing disk time, ensuring the database gets its guaranteed throughput no matter what the logging agent is doing.
It's amazing how much is happening beneath our feet. We haven't even left phase 1 yet. We need to shift gears slightly. We've talked about the kernel. Now let's talk about the interface to the kernel, the shell.
Bash. The language that refuses to die. The duct tape of the internet.
The roadmap insists that even in 2026, even with all this AI, Bash is still the glue that holds the entire world together.
It is. AI writes code, but Bash executes it. But they advocate for a very specific style. Defensive scripting. No more sloppy one-liners. They say you have to treat Bash like production code.
And they mention a specific incantation that every cadet needs to tattoo on their arm. Set DHEO pipe fail. I feel like I've seen this, but let's break it down. What does the DU do?
E stands for exit immediately. Standard Bash behavior is terrifying. If a command fails, the script just shrugs and keeps going to the next line.
Which is insane if you think about it. If my Python code throws an exception, the program stops.
Exactly, but Bash just keeps on trucking.
Yeah.
Imagine a script that copies a database to a backup location, and then on the next line, it deletes the original to save space. If the copy fails, maybe the disk is full, maybe permissions are wrong, but the script keeps going.
Oh no, it deletes the original and you lose everything.
You lose everything. -E stops the script the microsecond an error occurs. It prevents that cascade of failure. It's a non-negotiable safety feature.
Okay, that seems mandatory. What about you?
U treats unset variables as errors. This prevents the classic, and I mean classic disaster, where you try to run a command like rman-bash rf prefix.
Right, you're trying to clean out a specific directory.
You are. But if the variable prefix isn't set for some reason, maybe a typo in the variable name, maybe a network glitch when fetching it, Bash just sees rm-bash rf.
Which wipes the entire root file system. Game over, server's gone.
Correct. Meju acts like a safety on again. It stops the script before it can run that command if the variable is empty, another lifesaver.
And the last one, pipe fail.
That catches errors in the middle of a pipeline, a chain of commands. So if you run something like curl some Earl grep, secret awk, print $2. Normally, Bash only looks at the exit code of the last command, the awk.
So if the curl fails because the internet is down.
The script might still succeed because the grepanoc will just process empty input and exit cleanly. Pipefail says, if any link in this chain breaks, the whole thing is a failure. It makes pipelines robust.
It's all about failing fast. Don't let the error propagate and cause more damage. Okay, moving through phase 1, we touch on version control, and it looks like Git flow is officially dead in 2026.
It seems so. The consensus is that GitFlow, with its long-lived feature branches and complex merging ceremonies, is just too slow for modern CI/CD.
So what's the replacement?
The roadmap pushes heavily for trunk-based development, and specifically what they call the Microsoft release flow. The core rule here is fascinating and a bit counterintuitive at first.
What's the rule?
Code never merges back from a release branch to main.
Wait, explain that. If I fix a critical bug in the release branch because production is on fire, I don't merge that fix back into my main development branch.
You do it the other way around. You fix it in main first, then you cherry pick that specific commit to the release branch.
Why that order? What's the logic there?
It forces you to prioritize the future, which is main over the past, which is the release. It prevents that nightmare scenario where a hotfix gets applied to production but is forgotten in the dev branch.
Oh, and then you release the next version 2 weeks later and the bug reappears.
Exactly. A regression. We call that a regression loop. This flow kills regression loops by ensuring the fix is in the source of truth, main, before it ever goes to production.
That's really smart. It's a process guardrail. Finally, for phase 1, the engine room talks about networking, specifically inside Azure. What's the big takeaway for our cadet here?
It's the move away from public endpoints for everything. The standard is a hub-and-spoke topology, and the critical technology to understand is Azure Private Link.
So in the old days, you might connect to your SQL database over a public URL. It's secure. Sure, it has a password and TLS, but it's still on the public internet.
Right. Anyone on Earth can ping it. If there's a zero-day vulnerability in the SQL Server software itself, you're exposed to the entire world.
That good.
In 2026, that's considered malpractice. Payda services like SQL or container registries are accessed via private IPs, like 10.0.1.5, right inside your virtual network. The data never, ever hits the public internet.
It stays entirely on the Azure backbone.
Never leaves. It's a massive security upgrade. It's like having a dedicated, guarded fiber optic cable between your app and your database, rather than shouting your secrets across a crowded room.
All right. That was the engine room. We've got grease under our fingernails. We understand the kernel, the shell, the network. Now we move up a level to phase 2, the quality gate.
This is where we shift from how it works to how we build it. And the theme here, the big buzzword, is shift left.
Which we hear all the time. But what does it mean in practice here? Moving security and testing earlier in the process, right?
Exactly. But it's more than a buzzword in this roadmap. It's an architectural requirement.
Yeah.
Instead of security being a scary person who yells at you the day before launch.
Which is everyone's favorite experience.
Right. Instead, security is built into the automation backbone. And that backbone, for our 2026 architect, is GitHub Actions.
Now, the roadmap mentions a specific problem that plagues almost every large organization, YAML sprawl.
Oh yes, you see this everywhere. Every single repository has its own copy-pasted workflow YAML file. It's hundreds, maybe thousands of lines long. Someone fixes a security bug in one, but the other 499 repos remain broken. It's completely unmanageable.
It's copy-paste engineering.
At its worst. So what's the 2026 fix for that?
Reusable workflows.
Exactly. A central governance repo defines the standard build and scan workflow. It's like a library function for your CI/CD.
So my service repo just points to that central one.
Yes, your service repo just has a 2-line file that says, use the standard workflow from the governance repo. It's a write once, comply everywhere model. If the security team wants to add a new scanner, say a new AI vulnerability detector, they update that one central file.
And instantly, every project in the company is using it on their very next build.
Instantly. It's a dream for compliance and governance.
That does sound powerful. Now let's talk about secrets. We've all been guilty of putting a password in a GitHub secret variable somewhere, or even worse, checking in a .env file.
Guilty. We've all done it in the early days.
But the roadmap talks about OIDC authentication. This is meant to be the death of the long-lived secret.
This is the end of hard-coded static secrets in CI environments. OIDC stands for OpenID Connect. Think of it like a hotel key card versus a traditional metal key. A metal key works forever. If you lose it, anyone can use it until you go through the pain of changing the lock on the door.
And changing the lock is a huge pain. You have to rekey everything that used it.
Exactly. OIDC is like a hotel keycard.
Yeah.
When the GitHub workflow starts, it effectively walks up to the Azure front desk, Azure Active Directory, and shows its ID. It says, hi, I have this specific workflow running in this specific repo on this specific branch, and here's a token signed by GitHub to prove it.
And Azure checks the ID. It verifies the signature.
Azure checks the signature and says, okay, you are who you say you are. Here's a temporary access token. It's valid for 5 minutes. Go do what you need to do.
And after 5 minutes,
It vanishes. It's useless. There's no long-lived secret to steal. Even if a hacker dumps the environment variables during the build, the token is already expired by the time they can even look at it.
it reduces the window of vulnerability from forever to 5 minutes.
A massive improvement.
That is slick. So we have the pipeline automated and secure. Now we need the sentry standing guard at the gate. Sonar Group.
Right, and Sonar Group has evolved. It's not just a dashboard you check occasionally to feel bad about your code. In this roadmap, it is a hard blocker. They talk about quality gates.
So this is mechanically blocking the merge.
Yes. If your pull request has, for example, a rule that says critical issues must be 0, and Sonar Group finds 1 critical issue, the merge button on GitHub is literally disabled. You cannot click it. It's grayed out.
You literally cannot merge bad code.
You cannot. And they use something called a clean code taxonomy with a very strict definition of new code. This is important for dealing with legacy systems. A lot of teams say, oh, we can't use quality gates. Our old code is a mess. We have 10,000 existing bugs.
Right. We'll never pass. It's too daunting to fix it all at once.
Exactly. This approach says, okay, the old code is messy. We accept that as technical debt, but you are not allowed to add one single drop of new technical debt. The quality gate only applies the rules to the lines of code you changed in this PR.
So it stops the bleeding.
Stops the bleeding. It's called the ratchet effect. You can only get better. You can't slip back.
I like that. It makes it actionable instead of overwhelming. Now, before we package this application, we have to harden the container image itself. The roadmap strongly suggests distroless images. This sounds stark.
It is stark, and it's brilliant. A standard Docker image like Ubuntu or Alpine comes with a lot of stuff. It has a package manager, apt-get. It has a shell, bash. It has text editors and networking tools. A distroless image contains only your compiled application and its direct runtime dependencies. That's it.
So there's no shell, no bin bash.
No shell, no package manager, no curl, no racket, no else.
So if I'm a hacker and I find a remote code execution vulnerability in your web app and I manage to get in.
You're stuck. You're in an empty room.
Yeah.
You try to run bin bash to get a terminal. File not found. You try to run curl to download your crypto miner. File not found. You can't even list the files in the directory because walls isn't there.
It drastically reduces the blast radius of a breach.
It turns a breach into a dead end. It's like breaking into a bank vault, but the vault is completely empty and the door locks behind you. There's nothing to do.
And to make sure nobody tampered with that beautifully empty image, we have Docker Content Trust.
Right. Digital signatures for your images. The CI pipeline signs the image with a private key after it's built and scanned. The Kubernetes cluster is then configured with the public key to verify that signature.
So if someone tries to inject a malicious image in the middle, a man-in-the-middle attack, or maybe a disgruntled employee pushing a rogue image to the registry?
The cluster simply refuses to run it. The API server says, signature verification failed. Untrusted source. The deployment is rejected before it even starts.
So we've built the code, scanned it, hardened the container, and signed it. Now we need a safe place to store it. Welcome to Phase 3, the source of truth.
And this phase revolves entirely around JFrog Artifactory. And the core rule here is simple but absolute. If the artifact is not in the central repository, it does not exist.
No sideloading. No, I built this on my laptop and I'll just script it to the server.
Never. That is a firing offense in a Phase 3 organization. And we see a strict adherence to what's called binary lifecycle management. This means you build a binary once, and only once.
Why is that so important? I often see teams rebuilding for staging and then rebuilding again for production. Seems logical.
It seems logical, but it's incredibly dangerous because of dependency drift. Imagine you build for staging on Monday. Your build tool pulls in Library X version 1.0. You test it for hours. It works great. Everyone signs off.
Okay.
On Tuesday, you kick off the build for production. But in those 24 hours, the author of Library X released version 1.1 with a tiny subtle bug. Your build tool automatically picks up the new version because you specified a version range.
And now production is broken, even though staging worked perfectly just yesterday.
And you're deploying code you have never, ever tested. This is why we say, build once, lock it in a vault, and then promote that exact identical binary file from dev to QA to prod. It is immutable.
It travels unchanged through the entire life cycle.
Exactly. What you test is what you deploy.
That makes a ton of sense. Now, JFrog has a tool called X-Ray, and the roadmap emphasizes recursive security scanning. What does recursive mean in this context that's different from the SonarQube scan?
It means it goes deep. It doesn't just look at the label on the box, which is your package.json or your pom.xml. It unpacks the box. It unzips the Docker image layers. If there's a .jar file inside, it unzips that. If there was a .war file inside the
All
.jar,
turtles all the way down.
it's turtles all the way down. It finds the hidden transitive dependencies. A lot of the worst vulnerabilities like log4shell hide deep in the dependency tree. Maybe a library you use uses another library that uses a vulnerable version of log4j. X-Ray roots them out.
And the roadmap mentions IDE integration here, catching it even earlier.
Yes. This is the ultimate shift left. X-Ray has plugins that alert the developer while they are typing in their IDE. They type log4j.2.14.0 in their package.json, and a little red light flashes immediately. Hey, that version you just typed, it has a critical vulnerability.
You catch it before it's even committed, before it even exists in the codebase.
Precisely. It's about stopping bugs at the cheapest possible moment before they're even written. Now, there's a new concept in this phase called Release Bundles v2.
Yep.
This is moving beyond just deploying an image.
Right, because an application isn't just a container image. It's the image, plus the Helm chart, plus the database migration script, plus the configuration.
All of it. And if you deploy the new image but forget to update the Helm chart with the new environment variables the image needs, the app crashes. A release bundle wraps all of that, the Docker image, the Helm chart, the config files, into one atomic, immutable versioned package. It ensures that the configuration matches the code mathematically.
And there's a note here about air gap support. This sounds like spy movie stuff.
It's for high-security environments, defense, banking, energy grids, places that are not and cannot be connected to the internet. You can export this release bundle as a single, digitally signed file.
So you can put it on a secure USB drive.
Walk it across a room to a disconnected network, that's the air gap, and import it on the other side. The signature guarantees that not a single bit was flipped during transit. It ensures that the chain of custody is never broken, even when you have to physically move the bits.
Okay, we have our secure bundle. Now we need a place to deploy it. Phase 4, the target. This is the cloud-native orchestration layer.
And specifically in this roadmap, we're talking about AKS, Azure Kubernetes Service.
The first rule of Phase 4 is the end of ClickOps.
No more clicking in the Azure portal. If you are creating resources by hand with your mouse, you are doing it wrong. Everything must be infrastructure as code, IAC, using Terraform or its open source fork, OpenTofu.
Because if you click it, you can't version it. You can't reproduce it.
And you can't audit it. And if disaster strikes, you can't restore it quickly and reliably. Code is truth. Code is your recovery plan.
Now, one of the biggest security evolutions in this phase is workload identity. We talked about OIDC for GitHub Actions earlier. This seems similar, but for the pods that are actually running in the cluster.
It is exactly that principle applied to running workloads. In the past, if a pod needed to talk to Azure Key Vault to get a database password, you had to mount a service principal, which is basically a static long-lived secret into the pod's file system.
Which means the secret is just sitting there on disk inside the container.
Right. If someone compromised the pod, they got the secret. Game over, they have the keys to the kingdom. With workload identity, the Kubernetes service account of pod runs as can exchange a token with Azure Active Directory. It gets a short-lived access pass, just like the CI job.
So there are no static secrets stored in the cluster at all.
None. It is a massive reduction in the attack surface.
Let's look at the networking architecture again. The roadmap specifies Azure CNI. This connects back to our Phase 1 discussion on networking, right?
Yes, it's the practical application of it. Azure CNI Container Networking Interface flattens the network. In simpler Kubernetes setups, pods are hidden behind a NAT layer. They have fake internal IPs. With Azure CNI, every single pod gets a real IP address from the corporate virtual network.
So my pod is a first-class citizen on the network, just like a virtual machine.
Exactly. This makes observability and security much easier because you can trace traffic directly to a specific pod IP, and it works hand in hand with a JCC, the Application Gateway Ingress Controller.
That's a mouthful, as you see.
It is, but it's very clever.
Yeah.
Usually you have an ingress controller pod running inside the cluster that routes traffic. That creates a double hop. Traffic hits the external load balancer, then the ingress controller pod, then your application pod. AGC is a special pod that runs inside the cluster, but its only job is to configure the external Azure Layer 7 load balancer.
So it's like a remote control for the big hardware outside the cluster.
Basically, yes. So traffic hits the big Azure Application Gateway and goes directly to the pod's real IP address. You eliminate that extra hop, which means lower latency and higher throughput.
And guarding all of this, the final piece of Phase 4 is Azure policy.
Think of Azure Policy as the bouncer at the club door of your Kubernetes cluster. It integrates as an admission controller. So when you send a deployment request to the Kubernetes API server,
It gets intercepted.
it gets intercepted by Azure Policy, and it checks it against a set of rules. For example, a policy might say, no containers can run as the root user, or all container images must come from our corporate JFrog registry.
And if your deployment violates a rule,
The API server rejects it. It says denied. It never even gets scheduled. The infrastructure itself refuses to run insecure or non-compliant code.
we are building a fortress here, a very intelligent fortress.
We are. But a fortress needs a commander. That brings us to Phase 5, the orchestrator.
And the tool of choice here is Harness. Now, a lot of listeners might ask, why Harness? Why not just use the GitHub actions we talked about in Phase 2 for deployment?
That's the most common question, and it's a good one. GitHub Actions is fantastic for CI, for building and testing. But for CD continuous delivery, you need something more. You need a stateful orchestrator. Harness doesn't just run a script and forget about it. It manages the entire life cycle of a deployment.
And the roadmap says it manages the GitOps plus pipelines hybrid model. What does that mean?
It's the best of both worlds. GitOps, which is powered by Argo CD embedded inside Harness, manages the desired state. It's constantly watching to ensure the cluster's live state matches what's declared in your Git repo.
It's the reconciliation loop.
Right, but pipelines manage the process of getting to that state. The approvals, the integration tests, the security scans, the promotion from dev to QA to prod. You need both, state management and process management.
And having that process orchestrator enables these advanced deployment strategies we hear about all the time. Blue-green and canary. Let's differentiate those for the listener.
Okay, so blue-green is the safest, but also the most expensive strategy. You have your current version running in production, that's blue. You spin up a completely separate full-size environment with the new version, that's green.
A complete parallel stack.
A full clone. You test green internally. If it looks good, you go to your load balancer and flip a switch. All traffic now goes to green.
It's an instant cutover.
Instant. And if green suddenly catches fire, you just flip the switch back to blue. Instant rollback. The downside is you're paying for double the hardware for the duration of deployment.
So that's where canary comes in to be more cost-effective.
Canary is for the cost-conscious or for services at massive scale where a full blue-green is just not feasible. You don't skin up a whole new environment. You just deploy the new version alongside the old one and route, say, 5% of your real user traffic to the new version.
You're limiting the blast radius of a potential failure.
Exactly. If the new version is broken, only 5% of your users are annoyed, not 100%. You watch it carefully. If it's healthy, you slowly dial up the traffic, 25%, then 50%, then 100%.
And who is watching it carefully? That's the cool part. Phase 5 introduces Harness Ada, the AI development assistant.
This is our first real taste of AI in the workflow. Ada uses generative AI, the same kind of large language models we're all familiar with, for troubleshooting.
So when a pipeline fails, instead of me having to dig through 10,000 lines of logs to figure out what happened,
Ada reads the logs for you. It correlates the error message with the code changes that were in the deployment, and it produces a root cause analysis, an RCA, in plain English. It says, hey, your deployment failed. Why? Because the new Helm chart requests 4 GB of RAM, but your namespace quota is only 2 GB.
and does it suggest a fix as well?
It does. It will say suggested fix. Update the resource request in your values.yaml file or contact your admin to increase the namespace quota. It acts as a real-time tutor.
That is a game changer for the paper engineer trying to learn. It's teaching them the Phase 1 concepts like quotas at the exact moment they need to know it.
It is. It also helps with policy generation. You can tell it in plain English. We should not allow deployments on Fridays after 3 p.m.
A universal law of IT.
The most important law. And it will write the complex OPA REGO policy code to enforce that. It bridges the gap between human intent and machine implementation.
Okay, we have arrived. The final phase. The peak of the mountain. Phase 6. The nervous system.
This is where it all comes together. This is where we close the loop. And the tool we're using here is Dynatrace.
And the key technology is something called the One Agent.
The one agent is seriously impressive. You install it once on the host node, usually via a Kubernetes operator, and from then on, it automatically discovers and injects itself into every container, every process. You don't have to change your application code. You don't have to import a library. It just starts watching everything.
And it builds this thing called the Smartscape.
Which is a real-time 3D topology map of your entire system. This is crucial. It doesn't just see metrics. It knows that process A on host B calls service C, which then writes to database D. It understands the dependencies and the causal relationships.
And this brings us to a critical distinction the roadmap makes between the two types of AI we've discussed.
Right. We had Harness Ada, which is generative and probabilistic. It's great at language. It makes educated guesses. But here, in the nervous system, we have Davis AI. And the roadmap is very clear. Davis is causal and deterministic.
Why does that distinction matter so much?
This is the most important concept in Phase 6. Generative AI is amazing, but it predicts the next likely word.
Yeah.
It's creative. It can be wrong. You cannot automate a production rollback based on a guess. You can't say, I think the database is 80% likely to be the problem, let's restart it.
You need to know for sure.
You need to know. Davis AI is causal. It looks at that Smartscape topology map. It traces the wires of cause and effect. It says the user's login response time is slow. Why? Because the authentication service is timing out. Why? Because its connection to the database is locked. Why? Because the disk I/O on the host node where the database runs is 100% saturated.
It follows the chain of evidence, not probabilities.
Exactly. It is deterministic. And because it is precise, we can trust it to take automated action.
And that action is the closed loop, the self-healing system. Walk us through the final scenario described in the roadmap, the kill switch.
Okay. Picture this. It's 3:00 a.m. You are asleep. A new Canary release managed by Harness has just been rolled out to 5% of your users.
Okay, I'm with you.
Harness's pipeline reaches out to Dynatrace and says, how is the new version doing? This is called continuous verification. Dynatrace is using unsupervised machine learning to watch hundreds of metrics from that 5% cohort. Suddenly, its Davis AI detects a 50-millisecond increase in API response latency.
Which a human looking at a dashboard would absolutely miss. Or they dismiss it as noise.
A human would definitely miss it. But Davis sees the anomaly. It determines with certainty that it's caused by the new code version. It flags it as a regression. Harness receives that signal. It checks the automated policy. The policy says if latency degrades by more than 10% during a Canary, trigger an automatic rollback.
So Harness triggers the rollback.
Instantly, it reconfigures the load balancer to send 100% of traffic back to the last known good version. The incident is over in seconds. Most of the 5% of users barely even noticed a blip.
But it doesn't just stop there. It doesn't just fix it and stay silent.
No, this is the magic. Harness then automatically creates a JIRA ticket. It populates that ticket with the precise root cause analysis from Davis. It attaches the logs. It tags the developers who committed the code in that release.
So the engineer wakes up at 8:00 a.m. They don't have an alert storm. They have a single JIRA ticket in their inbox that says, we tried to deploy your code at 3 a.m. It caused a latency regression. We rolled it back automatically. Here is exactly why it failed. The system is currently stable. Please have some coffee and fix the bug.
That is the dream. The system heals itself before the customers even have time to complain.
That is incredible. It really is a complete journey. We started down in the dirt with PIDs and namespaces, the raw mechanics, and we've ended up with an AI that watches, analyzes, and fixes problems faster than we can even blink.
And that's the entire point of the roadmap. You cannot build a Phase 6 system if you don't understand the Phase 1 primitives. If you don't understand namespacing and coup groups, the AI's explanation of why the quota was exceeded won't make sense to you. You have to be an architect, not just an operator.
The roadmap uses a specific word at the very end to summarize this goal: anti-fragility.
Yes. It's a concept from Nassim Taleb. A robust system is one that resists breaking. But an anti-fragile system, it actually gets stronger when it is stressed. It uses failure as a signal to improve. By automating the recovery and automating the root cause analysis, we make the system stronger and smarter with every single incident.
And we change the role of the human. We aren't the fixers running around with fire extinguishers anymore. We are the designers of the system that fixes itself.
Which is a much better, more creative, and more valuable place to be. It frees us up to innovate rather than just react.
Absolutely. Well, that is a lot to digest. The 2026 Enterprise DevOps Roadmap, from the engine room all the way to the nervous system. I hope this deep dive gave you some aha moments and maybe a checklist for your own learning journey.
Keep digging into those namespaces. That's where the secrets are.
Always! Thanks for listening, and we'll see you on the next deep dive.